Hello, this video is going to review the Unit 4 practice exam. Number 1, a black body emits its most intense radiation at a wavelength of 185 nanometers. What is its temperature? This is a problem that can be solved using Wien's law that correlates the peak wavelength of an object's black body spectrum or its thermal radiation curve to the temperature of that object. So I know the peak wavelength in nanometers. I can just plug it into Wien's law and solve for T. And you get something that rounds to 15,700 Kelvin when sig figs are applied. Number 2, what is the largest momentum we could expect for a microwave photon? Microwave frequencies go up to 3.00 times 10 to the 11 hertz. So we are looking for a momentum. So that's something that we can associate with the de Broglie wavelength. The de Broglie wavelength is Planck's constant divided by linear momentum. So as long as I know how quickly this photon is moving, I can calculate its wavelength and set those two equal. So solving for P, I have Planck's constant in joule seconds as opposed to electron volt seconds. And the benefit to doing it that way is that you know a joule can break down into a kilogram, meter squared, and second squared. So ultimately, the way that the unit cancellation works out, you're going to be left with mass units and then velocity units. The product will give you momentum units. And I noted here, this value 6.63 times 10 to the negative 31, I think I just wrote negative 34 due to muscle memory, so I apologize for that. But the appropriate answer is 6.63 times 10 to the negative 31, and the units are kilogram meters per second. 3 is a photoelectric effect question. Nickel's work function is 5.00 electron volts. What potential difference must be applied to stop the fastest photoelectrons emitted by a nickel surface receiving 200 nanometer light? So we're given the work function, which is the minimum energy required to reach the photoelectrons that are the least deeply embedded in the surface. And I've converted that into joules because there are two different ways that you can solve this problem. So for one, the wavelength 200 nanometers, when I convert that to meters and then calculate the frequency, I get 1.5 times 10 to the 15 hertz. Method 1 involves using this energy conservation expression that we worked with in our photoelectric effect labs. That's both parts. And I am using it to figure out what the stopping potential is. HF is the energy that I can associate with the photoelectron after it's liberated. I can also think about that as the energy of the photon that actually is responsible for liberating a photoelectron. And then H times F naught is the work function. So working with joules, I would need to use the version of Planck's constant that is in joule seconds. So that's 6.63 times 10 to the negative 34. That energy is HF. Subtract off the work function, which is 8.00 times 10 to the negative 19 joules. And I'm left with a ratio. So V stop is equal to 1.945 times 10 to the negative 19 joules. And I've just divided negative E, where E represents the fundamental charge. When I do that, I get a negative. That is the negative that communicates that you are running a potential difference that will cause your photoelectrons to slow down as opposed to speeding up. And what we get when we apply sig figs is negative 1.21 volts. The other method simply involves using Planck's constant in electron volt seconds as opposed to joule seconds. And the approach is a little bit different when you get past this first step. So I have H times F. That's pretty much the same as what we did in method 1. Subtract off the work function. Now, when I solve for V stop, I have an energy of 1.21 electron volts divided by negative E. And because of the way that the electron volt is defined, it is literally just the charge of one electron multiplied by 1 volt. So going from electron volts to volts simply involves crossing out the E that's already inherently a part of the electron volt unit. So the negative arises for exactly the same reason as it did for method 1, and I get the same value, negative 1.21 volts. Here's another photoelectric problem. Sodium's work function is 2.30 electron volts. What is the threshold frequency for this metal? So the threshold frequency, that represents the borderline beyond which frequencies are just not going to be capable of liberating photoelectrons. And then on the opposite side of that border, any wavelength or any frequency that falls on the right side is going to be capable of liberating a photoelectron. So knowing the work function means that all you have to do is divide out Planck's constant. And I've done it both ways here just to demonstrate that you do end up with values that agree with one another, at least out to the second decimal place. So the rounding is a bit different, but I end up with something I can express as 5.56 times 10 to the 14, and this is hertz. Next, copper's work function is 4.40 electron volts. What is the threshold wavelength for this material? Will photoelectrons be emitted by that surface when it is illuminated by visible light? So any metallic surface is capable of producing photoelectrons, but we can't say that any wavelength of light will be capable of liberating photoelectrons from a specific material. I can start with the work function, and I have it converted into joules just to demonstrate that you can do this either way. I don't think I stated it before, but the conversion factor is that 1 electron volt is equal to 1.60 times 10 to the negative 19 joules. The threshold frequency can be found by taking the work function and dividing it by Planck's constant. So I used both methods to come to the conclusion that that would be 1.06 times 10 to the 15 hertz. And from there, the threshold frequency would have to correlate with the threshold wavelength. And the wavelength is what we got to see most directly when we were working with the photoelectric effect sim in the photoelectric effect part 1. Take the speed of light, divide it by that frequency, and you end up with 2.8302 times 10 to the negative 7, and that's meters. Multiply that through by 10 to the 9 to get it into nanometers. So we have 238 nanometers. That falls outside of the visible part of the spectrum. That runs from about 350 nanometers to about 700. So this is in the ultraviolet, in other words. So since this threshold wavelength is smaller than the smallest visible wavelength, visible light will not be capable of liberating photoelectrons from that surface. Number 6, what is the de Broglie wavelength of a 0.08 electron volt neutron? So this energy is something that I can equate to a kinetic energy because we're not talking about a photon, which is massless. Neutrons have mass. So I convert 0.08 eV into joules, and I look up the mass of the neutron, which is 1.67 times 10 to the negative 26 kilograms. That's not something that I would expect you to have committed to memory, so it would be on the formula sheet if this showed up on an exam. And then I could just take the kinetic energy expression. So one thing that's subtle here is that de Broglie wavelengths are associated only with objects that have mass and are not stationary. So I know the type of energy associated with this neutron would have to be kinetic because the neutron has to be moving. Rearrange that expression to solve for V. I have twice the kinetic energy in joules divided by the mass. Once you take a square root, you get a velocity of 3,915.27 meters per second. I don't just need to know how quickly the neutron is moving, but I need to know its linear momentum so that I can use that to figure out the de Broglie wavelength. So linear momentum is just mass times velocity. I am still just working here with Planck's constant in joule seconds because the unit cancellation is a little bit simpler than if I had done this with electron volts. What we end up with is 1.01399 times 10 to the negative 10 meters. And our answer is given in nanometers, so just multiplying this by 10 to the 9 gets me to that answer. And because the energy of the neutron was only expressed to 1 sig fig, the de Broglie wavelength can also only be expressed to 1 sig fig. 7. What is the velocity of an electron that has a de Broglie wavelength equal to 550 nanometers? The procedure is going to be similar to what we did in question 6, only this time we're dealing with the mass of an electron. So that is 9.11 times 10 to the negative 31 kilograms. And this time, I don't need to manipulate that de Broglie wavelength equation at all. I can just plug in the values that I have. So again, I stuck with Planck's constant in joule seconds just for simplicity. And when you calculate what the linear momentum of this electron is, you find that it would be 5.0105 times 10 to the negative 37, and those units are kilogram meters. Remember that a joule is a kilogram times meter squared over second squared. So when you do the full unit cancellation, 1 meter survives in the numerator, 1 second survives in the denominator. We're left with 1,300 meters per second. Eight. How quickly would a 62 kilogram human need to walk to have a de Broglie wavelength of 1 billionth of a nanometer? We can determine what the velocity is by starting with the de Broglie wavelength expression and just solving it for v. So we know that our target de Broglie wavelength is 1 billionth of 1 nanometer, so that works out to 1 times 10 to the negative 18 meters. When we plug that in, we find that the linear momentum of this human would be 6.2 times 10 to the negative 17 kilogram meters. And, that's not a linear momentum, but just mass times a wavelength. So kilogram meters would sort of be like a moment of inertia divided by a distance, but it's just an interstitial unit. We're going to use it to cancel some other things out, so don't worry too much about it. When we carry that out, you get 1.069 times 10 to the negative 17 meters per second. So we're shooting for our velocity in nanometers per second because this is going to be exceptionally small, but not zero. That's the key takeaway here. Since this human has a minuscule amount of kinetic energy, that person has a de Broglie wavelength that is calculatable using this method. So doing a unit conversion, that's where we get 1.1 times 10 to the negative 8 nanometers per second. 9. What is the wavelength of the photon that's emitted when an electron in a hydrogen atom undergoes a transition from n is equal to 3 to n is equal to 2? So we spoke about this a little bit in class. This is the H-alpha transition. In order to figure out what wavelength corresponds with that, we can determine the energies that correspond with each of the available energy levels in the hydrogen atom. So that's negative 13.60 electron volts. That's the binding energy for the hydrogen atom, divided by n squared. I have n is equal to 3 and n is equal to 2. So I can calculate those two energies, and they're both negative values. The energy difference between those positions is delta E. That is 1.8 repeating electron volts. I converted that into joules. Next, I took the Einstein's photon energy expression, E is equal to Planck's constant times the frequency, and recognize that frequency is the speed of light divided by a wavelength. Thus, the wavelength is h times c divided by an energy, where the energy is going to correlate with the photon that would have to be emitted in order for the electron to go from state 3 to state 2. I know what that value is. We can plug that in and we get 6.581 times 10 to the negative 7 meters. I have, technically 4 sig figs. So I could have kept 658.1 here, just going off of the 4 sig figs that I have for the binding energy. But regardless, when you have this value in meters, multiplying it through by 10 to the 9 will turn it into nanometers. Number 10, what's the frequency of the photon responsible for the n is equal to 4 to 5 transition in the hydrogen atom? So I'll backtrack for a moment because I didn't mention it here, but it is relevant. The photon that has to be emitted in order for our electron to jump from state 3 to state 2 would result in an emission line in the emission line spectrum that we talked about in the quantization chapter. So if a downward arrow correlates with emission, an upward arrow would correlate with absorption. So what we're doing is finding the frequency that correlates to an absorption line in the absorption spectrum. I need to know the energy associated with state 4 and state 5, and I can compute that the same way that we just did in question number 9. The energy difference between those two locations is 0.306 electron volts. Converting that into joules gets us to 4.896 times 10 to the negative 20. And now I'm using Einstein's photon energy equation, E is equal to h times F. So that means that F has to be E divided by H. And that's how we end up with 7.38 times 10 to the 13 hertz. Number 11, a 160-gram hockey puck is placed in a box that's 1.0 meter long. What is its 0 point energy? So unlike the classical physics that we talked about in semester 1 and the bulk of semester 2, this hockey puck that has a mass that's known is not going to have a stationary state that corresponds with E being equal to 0. To say that another way, there does exist a minimum energy that corresponds with the n is equal to 1 state. And that minimum energy is the 0 point energy we're looking for. So I can go to the expression for energy as a function of quantum state. E sub n is equal to n times this group of constants, h squared divided by 8m times L squared, where L is going to represent the length of our one-dimensional box. For n is equal to 1, I can plug in a 1 for those n values. And I've done this with Planck's constant in joule seconds. Again, just to make the unit cancellation a little bit easier on the step where I'm calculating E1. So the joule is being squared here. I've got kilograms squared times meters to the 4th power divided by seconds to the 4th power. When you do that unit cancellation, you end up with an energy in joules that is incredibly small, 3.43413 times 10 to the negative 67 joules. Now, note that the denominator of this expression that we have, 8 times m times L squared, that is something that we can think of as having the same units as a moment of inertia. Next, take that energy that's in joules and convert it into electron volts. So this time, since we're going in that direction, it's going to involve dividing by 1.60 times 10 to the negative 19 joules. And I end up with another incredibly small value, 2.1463 times 10 to the negative 48 electron volts. So if this were a value that we were going to attempt to measure in a laboratory setting, we'd find that it would essentially be indistinguishable from zero. Number 12, approximate the quantum level that would give the puck in the previous problem a 0-point energy of 1.0 electron volts. So I've expressed that in joules as well, and I want to point out the subtle difference between the 0-point energy that we determined in question number 11 and the energy that we are assuming here in question number 12. So if that 0-point energy were equal to 1.0 electron volts, finding the n, the quantum level that would allow for that to be possible, would involve taking that 0-point energy and then multiplying it by the reciprocal of the term that we used before taking a square root. Doing that shows that n should end up having no dimension. And if we look at the kilogram meter squared over second squared portion of that, we can see that that is a joule. So the numerator of this expression is joule squared. The denominator is joule squared. So solving that square root, we end up with 6.8258 times 10 to the 23rd. And that is a quantum level. So when we were talking about hydrogen energy levels, we didn't say much at all about levels above n is equal to 5 or potentially n is equal to 6. So in order for that puck to have a 0-point energy that's not enormously small, like we found in question 11, but instead is one single electron volt, which I should note is not a lot of energy. We're looking at 1.60 times 10 to the negative 19 joules. But still, the quantum level that would correlate to that would be approximately 6.8 times 10 to the 23. So I have a bit of a kind of a clunky, low-tech solution to the answer that I had for question 12. I had it expressed as n squared and forgot to take the square root. So taking the square root still gives you an enormously large number. And now that I am saying this out loud, I realize that for number 11, I didn't write n squared. It didn't affect our outcome because we were dealing with n is equal to 1. But the expression that we use in 11 is the same as the one that we would use for 12. Finally, 13. A simple harmonic oscillator in its ground state has a frequency of 3.00 megahertz. Later, its energy is found to be 1.55 times 10 to the negative 7 electron volts. What state is it in? So just to be clear, we're looking for the state that it's in when the energy correlates to the value that was given. So I have the ability to calculate the angular frequency for this simple harmonic oscillator, and I can use logic that's exactly the same as how we would approach this if we were discussing this in semester 1. So the period of that oscillator would be 2 pi divided by omega. And since the period is equal to the reciprocal of f, the frequency, omega is going to be 2 times pi times f. I can write that as 6.00 pi times 10 to the 6, and the units would be radian per second. The energy of our oscillator in its ground state is given in EV and joules here. And it's this expression that allows us to determine what state that energy is in. We're seeing something here that's fundamentally quite similar to what we saw when we discussed standing waves in boxes that had matching ends. In that scenario, whether the ends were both open or both closed, we found that it was only possible to fit half lambda multiples into that box. So using that same logic, E sub n would also have to land on some half integer multiple of h bar times omega, where h bar is just Planck's constant h divided by 2 pi. If I solve this expression for n, I find that E sub n times 2 pi over h times omega added to 1/2 will give us an n value. So I can plug in those energies. I chose to use joules in this scenario. So I chose 2.48 times 10 to the negative 26 joules. And as a result, I needed to use 6.63 times 10 to the negative 34 joule seconds. Regardless, you end up with 12.469 added to 1/2. When you do that, you get 12.97, which is approximately 13.